What's up, everybody? Welcome to System Crafters. I'm David Wilson, and today we're here for an experimental live stream. Let me cut this music volume down a little bit. Where we're going to do some live compiler hacking, continuing on a project that I've been working on for, I don't know, since probably February, I guess, which is the Mesche compiler. And I'll explain a little bit more about what that is in just a second. But the goal of these streams, I don't know how many of these I'll do. It's sort of an experiment for now, but what I ultimately would like to do is start producing videos about the work that I'm doing on this compiler and the language itself. But to do videos about what I'm doing, I wanted to sort of record some of the live coding that I do on it to sort of cut together and make a nicely presented video that explains the concepts and shows some of the work necessary to build the features. But you know, recording myself coding is not so fun unless, you know, maybe I'm doing it on a live stream, which is a lot of fun for me. So I decided to start doing a little bit of live streaming for this purpose. And I'm hoping that, you know, for people who join this live, it will be interesting and maybe fun to take part in what's happening. But I'm not really intending for people to go back and watch the recordings of the live streams. So these are more ephemeral than what I was doing before on the Flux Harmonic channel. And mainly because I would not want anyone to have to watch all the live streams to keep up with what's going on, because it was a little bit overwhelming for anybody who was trying to follow Flux Harmonic in the past. So the point here is that we're going to have these streams that are just, you know, we do the stream. There's a recording that you could find on the channel if you want to, but the goal will be for me to take these recordings and then cut them up into actual videos that are maybe like 20 minutes long or something. It's a lot more easy to digest. So we'll see how that goes. We'll see whether I stick with it or not. It's really just a matter of, you know, how well it works in the end. So thank you all who are currently here. Please feel free to say hello in the chat. I see my friend Alex is here already. Hey Alex, nice to see you. So if this is the first time you've been to this channel, maybe you saw the post that I made on Reddit, or maybe you saw it on Twitter. This channel has primarily been about system configuration using Lisp programs in the past, specifically Emacs and GNU Geeks. So the Linux distribution GNU Geeks. I'm sort of branching out a little bit more now into doing actual development of Lisp implementations, or at least this specific one. And I also want to start talking more about the various different Lisp and Scheme implementations to sort of figure out like what features of them are interesting, how you might be able to use them for developing certain types of applications, and then taking all that stuff that I learned to try to put it together into one really interesting Lisp implementation, or at least I hope it will be interesting. That has a certain set of goals, which we can talk about in a little bit. Hello to Zane, Zion, Thokal, and Anton. Thanks for being here. Zane says, will these be unlisted, then put into a playlist on the channel? Exactly. So that's the plan. Anybody who wants to come find the recordings and watch them, it should feel free. I'm going to create a playlist on the System Crafters channel called Mesche Live Coding or something like that. And I will have all the stream recordings be unlisted, but they will go into that playlist so you can go back and find them if you want to. Hello to Zir. All right, so Mesche. If you didn't notice, which maybe you haven't unless I've explained it to you before, Mesche is basically the word scheme shifted by 2 characters. And that's because Mesche is heavily based on Scheme. I personally feel that Scheme is like the most elegant of the sort of mainstream Lisp dialects. Now, obviously, you could say Clojure is pretty elegant too. It's elegant in its own way, but it's very focused on a specific type of application. Scheme is sort of a more general specification for, I guess, you know, implementing the lambda calculus, but it is sort of, you know, a more low-level, minimalistic spec, at least the core of it anyway. And I really like that about it. I like the design of Scheme, but I feel like the way that Scheme is designed, and the fact that you have SRFIs, SRFIs, the sort of extension specifications that add functionality to the language that some implementations implement, others don't. I personally would like to have a more, I don't know, it's hard for me to describe, a more cultivated implementation of a scheme or something like a scheme that has a very clear perspective on what stuff should be in the language and have, you know, nice features that are very convenient and are amenable to implementing the kind of applications that I want to write. So this is mainly an experimentation project for me. It's a lot of fun. I'm learning a lot from it. That's part of the reason why I'm doing streams and videos about it, because I think that the stuff that I learn would be interesting to other people. So I want to sort of digest the things that I'm learning from this project and then make videos out of it, because explaining things about first class continuations or writing an actual macro system or any of the more advanced functionality of a Lisp or scheme implementation could be pretty interesting to people, and people may learn from it. So I want to sort of share the knowledge that I gained from working on this project. Hello to Jovan, and hello to Peter and Ashraz. Nice to see you both. Ashraz says, how long until you write your own init? Mesche? No, that's not happening. Not gonna happen. Yeah. Well, I can't say it will never happen, because who knows, like I'll get bored at some point and I'll start looking for other things to do. But all right, so the goals of this language and compiler are basically that, well, there's some sort of, I'd rather call these principles maybe than goals. Maybe that's better to say just principles. Simple, the compiler and runtime should be easy to understand and debug. This may not hold true as time goes on, because the more advanced features I add to it, the more complex it might be, but the idea would be that a person could go look at the code and sort of understand what's happening. Extensible, the language would be extensible through macros, mesh modules, which are basically extension modules that are written in mesh, or maybe even some C components that you can pull into your project and use, which is no surprise if you've used any other language or ecosystem in the last 15, 20 years. Easy registration of C functions into the runtime, functions and types. I would say it needs to be possible to pull in C libraries, or at least wrappers for C libraries, because you can't really do much without that these days. And practical, it provides tools for building projects with this language. Also things that are including C components. And I've got a build tool to actually do this that I've written over time. And I need to get refamiliarized with it, because I haven't actually worked on this project in probably, how many months has it been now? 3 or 4, maybe 3 or 4 months that I worked on this. So I got to get refamiliarized with the project, and you're going to see some of that today, because I literally just compiled it for the first time this morning in a while, and I don't really know exactly how it's going to go. So we'll see. Ashra says, do you want to add doc strings to mesh? Doc strings are probably my favorite Emacs Lisp feature. Yeah, absolutely. This needs to be as introspectable as Emacs Lisp. Now, let me talk about, well, we can talk about use cases, and a lot of this will come out of it. So use cases for the language. I want to be able to use this language to develop hackable tools for creative work. I started doing this on the other channel that I have, Flux Harmonic, which I'll continue doing stuff on that channel as well, but I kind of wanted to focus the actual compiler development on System Crafters instead, because I think it has more of a specific Lisp focus, and people might be interested in that. But the goal for me, at least, is to be able to build tools for creative work, like video and music production environments, writing tools, task management, that kind of thing, similar to what you would see from Emacs. I want to take the model that Emacs brings to the table, very super hackable, very customizable. You can build your own tools inside of it, that kind of model, but then put that into creative tools and maybe even cross-platform tools as well. Also game development, maybe in, I can't remember, was it April? I think it was middle of April. I did the Ludum Dare 50 game competition, and I used Mesh to do that game competition, and we actually got a basic game running. So you can go find those videos on the Flux Harmonic channel if you want to check it out. I'm planning to do more of that. I may actually do the Ludum Dare that's happening in September. Some of the work we do here may actually, well, I guess it's already almost middle of September. When is that happening? Let's see, Ludum Dare Game Jam. Ludum Dare, who knows what it's pronounced. Okay, so it's 25 days from now. I mean, we may still do it, because I had a lot of fun doing that last time. It was pretty grueling. Did, like 8 hours of streaming 2 days in a row. But yeah, worthwhile. But yes, the language should be good for game development. Also potentially mobile application development. If I were to make tools for like note-taking or task management or something that work on the desktop, I would also want them to work similarly on a mobile phone. So that's something that we'll look into later, I think. Zane says, I think if the viewers want some good background for these streams, they should check out Crafting Interpreters by Robert Nystrom. Yes, absolutely. There's a link to that in the description below. I've got a link to the Amazon page for that. It's an affiliate link. It helps the channel if you buy a copy of the book from there. But that book is actually what got me to write the initial implementation of Mesh, because it goes through implementing the same language, an interpreter from the same language in 2 phases. The first phase is just a pure interpreter in Java. And then the second half of the book, really the second 2/3 of the book, is an implementation of the same language in C, but you're writing an actual bytecode compiler. So you come up with your own instruction set for the bytecode VM, and you implement the whole VM and the language and compiler on top of that. And that's effectively what I did with Mesh. I just followed that book just chapter by chapter and built up a scheme-like language based on what I was seeing in the book. And it turned out really well. I'm really happy with where I got. And then I started adding my own functionality to it, like tail call optimization, module system, a lot of other stuff that wasn't covered in the book. So it was an excellent foundation for me to get started writing my own language. So if you're a person who's interested in creating a compiler yourself, Crafting Interpreters is like the best book I've ever read for that kind of thing. I kind of feel like it's the best computer science book I've ever read because it's very approachable. The author does not use academic language to describe things. It's very straightforward language and extremely good examples, extremely good flow of how everything happens in the book. So really, really good book. You should definitely check it out if you're interested in that kind of thing. I've also got a couple other links in the description. One is for the book Lisp in Small Pieces, which is a very important book if you're interested in Lisp language implementations, basically. It covers both Common Lisp and Scheme, showing examples of how things are implemented in both and explaining to you sort of the concepts involved. It's a bit more academic because the person who wrote it is a professor, but super helpful if you really want to know how things are implemented for Lisp or Scheme. So I've been following that as well. I've been reading the section about continuations there recently. Super helpful. Also a little bit hard to digest sometimes because continuations are a little bit weird, which we'll get into in a little bit. But yes, that's also good. So that was a little bit of a tangent on books. But going back to the original point that Ashras brought up, because I want to make hackable applications, which is what I was describing here, making hackable tools. To be hackable, you have to be able to introspect into the tool to find what functions are available, what sort of global variables are available, at least in the context of Emacs. You have to find documentation for pretty much anything in the system so that you understand enough to write your own extensions to it. So documentation in the language, being self-documenting is very important. So we will add that too. It's another thing for the to-do list, basically. In the short term, we have a lot more important work to do on the fundamentals of the language and the compiler. The thing that I want to look at today is implementing continuations, leading up to being able to implement first-class continuations, because at least for Scheme, that is well, it's a language primitive, but really it's like an evaluation primitive that gives you the ability to do things like implement exceptions, implement concurrent code handling for like channels or async or all kinds of stuff like that. So it's very important for more advanced coding patterns, and it sort of will form the foundation of how I want to approach building user interfaces, event loops, lots of other stuff like that going forward. So it's something that I want to dive into and understand better, because I'm no expert on that. I have not implemented continuations before. This will be my first time. So we'll see how that goes over the next few streams, however many streams I end up doing for this. And we'll go further. But also we need things like macros and more standard library functionality. There was something else that's pretty important that I can't remember. I mean, obviously debugger and development tools. I have a REPL, very basic REPL, but we sort of need debugging capabilities there. So, hello, Thelemotheu. Yes, System Crafter stream in your daytime. It's also in my daytime, which is part of the reason why we're doing it at this time. I'm happy to see that there's at least 16 people here on YouTube, because this is not in the normal time that I do System Crafter streams. So nice to see that there are folks here today. All right, so should you use this? Probably not. This is an experimental project even for me. I've written a fair amount of code in it already, which has worked pretty well, but since things are definitely going to change, especially once I start adding macros and get continuations implemented, there's going to be a lot of instability, and the way that things work will change. So this is more of just a curiosity. If you want to clone the code, try to build it and use it a little bit, that'd be cool. I'd be happy to have any feedback anybody has, but definitely don't use it for writing anything yet. At some point in the future, though, I would be interested for people to try it out. But that's just for now. So I'll just give you a little bit of an overview of what I've implemented so far so that you have context about what we're going to be looking into. Peter says, working day starting, have to go shortly. Well, it's nice to see you here for the short amount of time. I appreciate it. So the things we have so far is that we compiled directly to bytecode running on a custom VM. So I have a VM implementation, and that's not like, what you think of when you have like a full computer VM that can run an operating system. This is just a simple implementation of a computer, a machine that has a specific instruction set, which is a very high level instruction set. The compiler converts the actual code that you write into this instruction set and then runs that instead of trying to interpret the code directly, which makes it a lot faster, and some aspects of the design of the VM also make the code execute a lot faster. Peter says, how does crafting compilers compare to the Dragon Book? I haven't read the Dragon Book, so I don't have any perspective on that, but somebody else may have an answer for that. So yes, having the custom VM is pretty useful, and that's where a lot of the work we're going to have to do on continuations will occur, because we have to change the model of execution that the VM currently uses to accomplish this. Also, we have first-class functions with closures, which is pretty important for a scheme implementation. So basically, you can just define a Lambda function anywhere, pass it around wherever you want, and then the environment in which that function was defined is carried along so that you can access variables that were there whenever the function was defined effectively. So just closures. If you understand what a closure is, that's basically what it is. Also, I have a tail call optimization for writing recursive algorithms and loops. Tail recursion is pretty important in Scheme because the first looping primitive that you have in Scheme is recursion. So a Scheme-like compiler would not work very well if it did not have tail call optimization. And that effectively is when in certain parts of the code, the compiler can detect whether the function call at that location can basically replace the current call for the call stack frame, so that you don't consume new call stack entries for each function call from that point forward. So basically, the way that it checks for that is to make sure that the return value of that function is not being stored in a variable or used somewhere else. So it is very nice for writing an infinite recursive loop, which I was using for writing a game loop in my game engine Substratic. So you basically have a function that keeps calling itself over and over, and it's not a problem because it doesn't actually create stack frames each call. So then we also have a module system, and modules can be defined and loaded into Mesh projects. So there's just a simple syntax for defining a module, but we also have the ability to load them from a load path effectively. Also have record types with fast setter and accessor functions. So a record type is effectively just a type where you have properties on it to store information, and that type has its own identity. Eventually, what I'm planning to do is to replace this with something like the Common Lisp object system, because I feel like there's a lot of benefits to be derived from the way that CLOS works, because you can have a more clear set of verbs and nouns in your language, where the nouns are the types that you have to operate on, and the verbs are the types of operations that are executed against those. So in Scheme, if you look at documentation for Scheme, you'll see a lot of places where there are very, very specific function names that are like number to string, or some type with some action name after it as a function name. So byte, what is it? Byte array dash something. There's a lot of functions like that, and there's sort of namespacing functions based on the type they relate to. I would prefer to have a language where you have one understood operation that could be applied to multiple types, and the way that Common Lisp object system works does allow you to do that. So you're basically defining classes that have generic methods that can be specialized for a particular class. I think that could be pretty interesting for things, especially like games and user interface code. So I want to experiment with that at some point. We probably won't get to that early because we need to do some more fundamental work, but it is going to be pretty important for the design of this language. That's where we're going to be deviating from Scheme a lot. The core language primitives, the primitive types and whatnot will all be part of this system, so that these generic functions can operate on them. And you could also define new functions to generate on the common types as well. Native function registration for integrating with C APIs. This is part of what we do for implementing the standard library. You have to call in the C functions, but also it can be used for writing wrappers around like OpenGL or anything else. I want to provide a better interface for that though, where you could define your wrappers in Mesh and then have that generate C wrappers that then can be compiled and then used. It would be even better if you don't have to compile them. If I could just make it like, you could dynamically define a binding to a C function and just call it. It's possible to do that, but at the moment, I think it would be easier just to compile down to the C code. Hello to John, nice to see you. Also, supports running a VM per OS thread. I haven't actually tested this yet, but the way that the compiler is implemented, there's no global state that should be used for the compiler. There's an object that you pass in for all the function calls. So we should be able to run a VM per OS thread, which means we have the ability to do some parallelism. And then having some of the continuation stuff would allow us to have some interesting interplay between threads, I think. But when you start dealing with multiple OS threads, you also need to worry about concurrent access to data structures. And one of the things I do want to add, which I should add to the future features list here, is a set of persistent data structures a la Clojure. Because I really like what Clojure does with using persistent data structures for maps and arrays. Pretty much just those. I mean, like, you do a lot in Clojure with just maps and arrays, which, is pretty nice for the kind of things that Clojure is meant for. I would also like to have persistent data structures, and they may even form the basis of the objects that you define. So the objects themselves would be immutable by default. And if you want to change them, you actually have to update, where you have to run a function on the object to get a new version of that object back. That does actually have a lot of implications on how you write code. So we'll have to experiment with it to see exactly how that's going to play out. But I'm pretty excited about implementing that. I've been reading the book called Purely Functional Data Structures, and it talks about how to do some of these things. It's also super academic and a little bit hard to wrap your mind around. I found it kind of boring, so I started reading Lisp in small pieces instead. So anyway, I'm going to get back to that because I do want to have something like that in the language. That's something that Scheme does not have by default. I mean, you could say that const cells are a persistent data structure, but you can actually set the car or the cdr of a const cell, so it's mutable. So yeah, and they're also not very efficient when it comes down to it. I mean, having to change a linked list using const cells, you have to recreate all of the entries leading up to that place where you want to make the change, which probably is the same for other persistent data structures as well, but I don't know enough about it yet, so we'll figure that out when we get to it. So eventually I want to have support for Windows, Mac OS, and Android, obviously. I need to be able to do that. Continuations I mentioned, we definitely want to have continuations. Hygienic macro definitions following Scheme's design. So I kind of want to use defined syntax. Define macro or def macro, unhygienic macros may be necessary at some point because there's just some things that are easier to do with that. But I kind of would like to see how far I could get with defined syntax and the sort of that syntax definition style that Scheme uses. I feel like it might be easier with that to make good compiler errors for whenever something goes wrong in a syntax definition as opposed to what you do currently with def macro, but I could be wrong about that. That's just sort of a theory I have. Authoring C APIs directly in Mesh. I mentioned that before. APIs for working with dynamic arrays of C structures. That was sort of a performance thing that I wanted to add. I found a really cool paper by Kent Dybvig, I think that's how you pronounce his name, about something called, I think it was F-types, a way to define in Scheme direct mappings to C data structures and to use them at runtime and even introspect on them. So we might try to implement something like that in the future. I think it'd be pretty fun. Okay, so Ashra says, doesn't Mesh's printing functionality currently use unlocked, non-locked access to standard out, standard error that might pose a problem for MT? Yes, that we would have to deal with that for sure. John asked for concurrent stuff. Does that also include STM? It would have to, includes some probably. I would need to look into that a little bit further though. Thelimotheu says, sounds like some good bedtime reading. Yeah, I think you're talking about purely functional data structures. It is, you could look at it as bedtime reading if you wanted to fall asleep, but it's not that bad. It's just, you know, at the time, sometimes I'm looking for inspiration. I'm looking for something to get excited about, like some kind of idea or thing to implement. And when I was reading purely functional data structures, it didn't really give me that. So I went to read about continuations instead, in Lisp in small pieces. All right, so let me take a little drink of water here, and then we can get started talking about continuations. So the goal is to implement first-class continuations like they are implemented in Scheme. And by that, I mean the way that code is, or the way that functions are executed in Scheme is that you, well, if a Scheme implementation uses continuations, or even a Lisp implementation uses continuations, the idea is that when you call a function, the place where that function was called is also represented as, or the remaining code after that, where that function was called is, or let me start at a more straightforward example. Imagine you have a function that you've written. Somewhere in that function, you call another function. So normally what happens in a language or runtime that does not use continuations is you create a new stack frame for the function you call, you go execute whatever happens in there, and then it returns a value back to the original function and then continues executing from that point forward. With continuation, something different happens. In that function you defined, you have your function that you're calling, and then the code that comes after that call location or that call site is represented as another function that then the function you're calling has to call with the return value. So instead of it being a linear execution of functions inside of another function, you're actually chaining together a bunch of functions. So that function that you call to return the return value is called a continuation. And this gives you the ability to have a bit more control over how things happen if you have the ability to get access to the continuation of the current function. So if you can get access to the continuation, then you can control when that function gets invoked, which means that you can save it for later. You don't have to invoke it right now. You can invoke it at some time in the future. So maybe if you want to implement some kind of asynchronous processing, you can call a function. That function can get a handle to the continuation at that current point, and then do some work, and then things could be going on for a while, and then eventually it will call that back, and then the function, the original function that you were calling from, will resume with that return value. So it's a little bit harder to reason about if you haven't thought a lot about it, and I still haven't thought enough about it that I'm like an expert at continuations. It's definitely broken my brain in the past. So we're gonna try to implement this because I feel like it will give a lot of extra power to the language, give us a lot of possibilities for things we want to do. Now, let's talk about how things currently work in the language. So I'm going to go to the VM because this is where the code execution actually happens. So the actual execution happens in a loop inside of, let's see, it's not in call. Let me see, do I have, all right, good. Language server is working. Let me see if I can find what the function is for that. Is it run? Yeah, mesh VM run. Okay. So this function is effectively just a loop that looks at all of the possible opcodes for this virtual machine. And for each one of those, it does some specific part of the implementation. So this is a stack-based VM, which means that for all computations, there is a stack that's shared by everything in the VM that's running. And it's not a call stack, it's actually a value stack. So you push the parameters to functions onto that stack. You also push the return value of functions onto that stack. So this stack is sort of the temporary storage for inputs and outputs of functions. So you see things like, you know, stack push, stack pop. These are taking things, putting things on the stack, taking things off the stack. Now there's a separate call stack as well. I think that the stack actually does sort of partly represent the call stack because you have the functions you're calling on the value stack as well because they're there to be invoked. But I need to refresh my memory on that a little bit because it has been a while since I've worked on it. So the important things are like the OP call for what it is that we want to change. So OP call is what invokes a function. It would be helpful if I actually showed what some of the output looks like. Let me see if I can jump into one of the tests. Test VM. Let me show what some of the opcode strings look like. Oh, not in this one. It's going to be in compiler probably. Okay. I'm testing some of the translations of things here. Okay, so if we have this simple function here, we're defining a function called testfunc, then we're calling nextfunc. Yeah, this is not being evaluated. It's only just being compiled down to bytecodes, and we're just sort of checking that out. So it's got some stuff where it's reading global variables, reading local variables, but then it's got this OP call here. And that's for the next func. So I think the read global is pulling out this next func. So it's sort of like considered to be a global value because it's not in the current lexical scope inside this function. And then the read local is for pulling in the value of the X, and then we do OP call. So now we have the value of the next func, which is a function, and then we have the value of whatever X is pushed onto the stack. We use OP call to invoke that next func, and then we pop that off the stack because what we're actually doing here is calling it in the middle of a function. We're not doing anything with the value. So after that call happens, we just pop the value off because we don't want it hanging around on the value stack because something might consume it by accident. So for continuations, the way this works would actually be quite different. And this is the place where we're going to have to think a lot and maybe experiment with some things, because I don't know yet how we're going to implement this. We're going to think about it. We're going to try to do whatever we can to get it implemented based on what we understand about continuations. So in this case, based on what I was telling you before, this call to next func would actually have to take whatever comes after in the function as a function that gets returned. So if we were to update this code to do that, what we would need is next func would take the X parameter, but it would also take a function, lambda K. And K is kind of a convention in, well, maybe we should go into a sample file. Do I have a sample file here? There we are, samples. Continuations.msc. And I'll copy this into here. Let's just paste some actual code so it's easier for us to write it and look at it. Okay. All right, so this would look like lambda k, and then we would have next func inside of this function. So the idea is that, oh, and then test func itself also would have a continuation function, which we represent as k, I think. And we would call k with the result of next func. Actually, no, I think that has to go all the way through. Whoops. Yes. So this is it's pretty weird how, excuse me, how all this works. So we would actually pass this k, k1, because we don't want to capture the wrong thing. So when you call next func is going to, sorry, test func is going to call next func, and it's going to pass the rest of the computation as a lambda to next func. And then inside that lambda, we're going to return this value. So we could return the value in theory. And then when we call next func again, we're doing a sort of like a recursive call. I probably should just do, let's see, just so it's not confusing. And then second func, when it finishes, it's going to call the continuation that was passed into test func. Because the idea there is that whoever called test func should, whenever the function, this whole function returns a value, we're actually doing it by calling the continuation that was passed into the original function. Hopefully that makes sense. We'll have to think about it a little bit more also. Anak says, please continue spreading high quality education stream. Big fan of your content. Thanks. Yeah, well, I enjoy doing it, so I'm gonna keep doing it as long as it's fun. Okay, so that was a very simple example. Now let's look at some other ways we might do this. If call. And we won't pass any parameters here, but we do need the k parameter for calling the result. So what I want is to try to think about how an if expression would look. So if, let's give a value here, another x. If less than x, so if x is less than 5, we need to, let's say, display it's less. Display, well, we want to return something. How about we do this? 150. This is a bad example. In fact, let's make it a little bit better by saying 100. And then add y to it, and then we'll subtract y from 50. Okay, so now that we have this set up, there's a few things we have to do to make this work correctly in the context of continuations. So first of all, the predicate of this needs to be evaluated first. So if we want to do that, when we invoke the predicate, we actually have to pass a continuation to the predicate at the time we invoke it. So it would look more like less than x5 and then a lambda k1, and then we need to do something with the rest of the computation. But in this case, if has specific parameters here, we need to check that value. So we need some kind of lower level if, I don't really know what you would call it, and we would check the value of k. Well, let me see. I think that's right. So you call that with the result value. Now we have the result value. We're checking k1. And then if k1 is true, then we're going to invoke the plus operation with 100 and y, but then we also need to pass something else along. So we're going to pass the k that was originally there because we're going to evaluate this branch of the code, but we need to pass the result. Since if returns a result from either of the branches, we need to pass that back to the place where this was called originally. Same here, we also need to say 50yk. And I think that would work. So really, it's all about the evaluation order in that case. We need to control the order of, or we need to follow the order of evaluation for any expression, and we have to use these intermediate functions as a way to pass the return value of each step of the evaluation on to the next part of the evaluation. Now, the way that I've actually implemented Mesche in bytecode sort of follows this already. So if we were to go into the compiler tests, let's see, if. Tail call if expression, that could work. Ifs are currently implemented as jumps, in fact. So let's see. I want to just have a more simple, okay, compiles if expression. So what happens here is that the predicate for the if operation is written first. So if this actually evaluated an expression, that would happen here. But since it's just t, we're just throwing t directly into the output of the compiler. Then we use this jump if false. And what we're basically saying is at this location, if the value at the top of the value stack is false, then we need to jump ahead some number of instructions in the current function. So what that would do is basically jump all the way down to this pop right here. Because if you evaluate this and it's false, you want to evaluate the false branch of the if expression. So that's when we have a jump all the way down to this pop and then run the constant. We were calling pop because we want to get that evaluated t off the value stack before we add on the expression for the false path. But if it's true here, we keep continuing forward to the next thing, which is a pop. Like I said, we want to get that, that predicate value off the stack. Then we have OP constant 0, OP constant 1, which basically in this function, we're storing constant values for literals that are here. So this is 3 and 1, which are literal values, which aren't stored in a variable. So they gotta be stored somewhere. So we have a constants table for this function. So we're pulling constant 0 and constant 1, which are for 3 and 1 here. Then we're calling add on top of that. So as you can see, we're evaluating all of the parameters to a call before we actually evaluate the call. So we already have our bytecode written out in a sort of backwards order that mirrors what we're doing already, or what we would like to do with continuation. So it might be the case that it's not so hard to implement continuations efficiently, because maybe inside of a function, we can just write out the code as we've been writing it so far and not have to do any kind of intermediate translation. So when I say intermediate translation, there is a common pattern for compilers, regardless of whether they actually use continuation as a language feature, called a CPS transformation, which is a continuation passing style transformation, which means whenever you parse all of the code for your language, you actually translate that into an intermediate form of the language where everything looks like continuations, where all functions take a function as its last parameter so that you can call that to pass a return value. So we may not have to do that. We may be able to go directly to bytecode. It would be really nice if we could do that, because it would simplify how we implement everything. So I'm hoping we could just sort of do a direct compilation to this and maybe just change some aspects of how the code evaluation works to get there. LMFAU says, we'll have to catch the rest later. Zoom meeting to finish the workday for me. Appreciate your content. Thank you so much for being here. I appreciate it. Hello to Mjolnir. Nice to see you. Okay. So as I said, we seem to be in a good position here to implement continuations more or less directly. Now, I don't know if that's entirely true. We'll have to sort of step through it and think about it a little bit. But at least for the case of the if statement, it does sort of make sense. Now, what would I need to do in bytecode to make a continuation work? I'm gonna have to think about this for just a second. So first of all, the most obvious thing, at least in my mind, is that this OP return, we don't have returns whenever you have a continuations-based evaluation system, because you're never coming back from a call on the call stack. Now that isn't true when you're calling out to foreign functions, like from the C libraries that you call into, but we're not gonna worry about that right now. We're only thinking about things in the space of Mesche itself. So OP return is the first thing that has to go. We have to replace it with something else. And basically what that is to replace it with a call, or more appropriately, a tail call. So here, this would actually need to be a tail call. So we say tail call. I think tail call, it's a check call, and if it's gonna have, is that the number of parameters? Probably it is. Yeah, so this would be a check call. And then it would have one parameter, and what else is in that function? Tail call. Yeah, so I would need a 0 there, because I think the 1 here represents the arity of the function of the required parameters. So how many required parameters are in the call, and then the 0 is for keyword parameters. This actually did implement keyword parameters as well, something I didn't mention before. So at this point, why is it complaining? Unterminated function like macro invocation. Okay. I think I'm calling it, nah, that's weird. Whatever. So tail call, let's just jump back. Okay. So at this point, we would need a tail call into the continuation function, which means we need to have it already. This if expression does not have an explicit continuation parameter. It has to be a detail of how the code is executed. So whenever a function gets called, let me just write down some thoughts on this. Whenever a function gets called as part of call stack, I'm gonna put stack in Well, as part of call initialization, we also need to store the continuation function. So let's go look at the VM really quick, because I need to see what we do for setting up a call. So I'm going to go to the VM call function, and this is the function that basically takes in the closure that we're going to invoke, the number of arguments that are going to be passed into it, the number of keywords that you pass into it as well, and then whether it's a tail call. And it just basically sets up that call. Now, there's a lot of work that goes into this at the very front, where we're checking for keyword arguments and checking against what keyword arguments the function supports, and then putting them in the right order so they can be indexed correctly. So we're going to skip that because it's not really important right now. What we do need to look at, though, is right here at the very end, where there's this if branch for if is tail call. So if this is going to be a tail call, we need to set up the call frame appropriately. And for tail calls, at least, we just reuse the existing call frame, which is what we would do in the case of a continuation as well. So we reuse the existing frame. So up values are basically captured closure values. So we just close out those values to capture them effectively. Copy over arguments. And then we reset the top of the value stack to shrink it back to where it was before. But we also make sure that the return value of the previous function is at the top of the stack. So really, it doesn't seem very different for the case of a tail call, which a continuation invocation would be. So maybe it's not that hard, actually, to implement continuations on top of the existing virtual machine. But what we do need is to set up the continuation function that needs to be invoked. So call frame. Let's see if we can jump to the definition of call frame. Okay, so call frame has a closure. It has the instruction pointer, which makes sense because you need to keep track of that as you're executing through the function. It has the slots for, I'm not sure if it's for constants. Can't remember the detail on that. And then the argument count for the call itself, because we need that to reset the stack whenever we do tail recursion. Dan Jones says, ESPN needs to run compiler sports. I think that the usual ESPN fan probably would not be interested in that, but it would be cool to have a channel that was focused on, different people writing compiler stuff. Hello to Aitor, Hunter, and Dan. Nice to see you all. Okay, so we also need a continuation, I believe. But whether it gets stored in the call frame or on the stack itself is a different story. So I need to think for a second about how this would work. So this is not the point where it matters. This is just sort of setup, but maybe it would help to go look at OP return, because that's where we return from a function. This is where we would change how things really operate in the way that functions are evaluated. So in OP return, this is usually happening at the very end of a function definition, because there's no explicit returns in a Lisp language, usually. I mean, it's just every expression returns a value, and then you sort of implicitly return the value of the last expression from any block, like a begin or a progin or lambda itself. So this OP return is sort of implicitly written out, or it's written out by the compiler, but the user does not write this in their own code. So when OP return is encountered, we store the value that is basically the return value of the function. So that's the thing that's at the very top of the value stack. We pop that off the value stack. We close out up values for any function locals that have been captured. So if there's any function that was defined inside of this function that was executing, we capture those values so that the function that now has a closure with them can still access them later when it gets called. Because maybe you're making a factory function that returns functions that are closing around values that are defined in that function. That function is going to get called later, so we still need access to those values and to set them and read them again, that kind of stuff. So if we're out of call frames end execution, so basically that's the point when the program is just done. But otherwise, we need to reset the value stack to where it was before the function was called. And then, let's see, there could be a stray module in the stack. Yeah, that's some sort of internal stuff. Then we store the previous result value, call frame, and value stack pointer before continuing execution. So the way that it would normally work, if you're not doing a tail recursive call, is when OP return gets invoked, we take all of the values off the stack where the current function is being executed, and then we're sort of ending up back where the previous function was executing with that result value on the stack, so we can continue executing where it was before. And that's sort of the interplay we need to figure out here, because we're gonna have code that looks like it's written synchronously without using callbacks, like, you know, continuation callback. But we need to write out the machine code or the bytecode in a way where it is actually asynchronous, or not asynchronous. It's using a callback for the continuation value, the result. And also the question is, do you even need a call for that? Or can you just swap out the current function and get back to where you are? Azer says, are you using LSP mode or eglot or something else for this? I'm using eglot with the ClangD language server. Coffeehouse Philosopher says, I found what I needed. Sorry, I missed what you said before. Not related. Is there any recommendations for an Emacs workflow when working with Java? I know that the LSP mode has a lot of support for Java. I haven't really done any Java dev in the last 20 years, I guess. Maybe. So I don't know much about what the Java situation is with LSP mode, but I know that one of the maintainers, I think, does regular Java development, so there's pretty good support for that. Okay. So I'm trying to imagine what it would look like to implement continuations without actually having to create a new function for that purpose. The only time you would need to create a new function for that purpose, I think, is when someone calls call with current continuation, you would need to wrap up that current state into an object that can be invoked later. And that's where things get tricky, because you need to save the state of the value stack so that it can be returned to at some point. And the thing is that you don't know when someone's going to do that. So is it the case that you would have to just do everything as continuations, which is going to be basically an explosion in the number of function objects that are being allocated, because you would need a function object for every place where the code branches or when you have a call in the code, which is a lot. So I'm trying to think if there's a way to do this efficiently, where the only time you need such a continuation object is when someone explicitly asked for one. Because otherwise, you don't really need to hold on to that old state. I mean, one of the goals of Mesh is to be efficient, to be fast. You know, not be just a normal interpreted language, but to be fast enough that you could use it for writing real code. And through the excellent teaching of the Crafting Interpreters book, I actually do have something that's pretty fast as a result of that. So I want to kind of continue on that path as much as possible. So let's assume for now that we're not going to have call with current continuation, a function where you can get the current continuation on demand. The current evaluation model is kind of like that, because for continuations, should have like a notes file probably. Let's just create one really quick. Mesh continuations notes. Or yeah, let's just say notes, whatever. So for continuations, the execution model is call a function, it runs some computations. When the function is complete, call another function to return the result to the remaining code of the call site, original call site. So we already sort of do this, which is basically a return. We just don't have to model that as a function call to do it. So in this case, we're leaving the value on top of the value stack and just resetting the stack. We're just clearing off the current call frame effectively from the stack so that we go back to the execution point of the previous function because the instruction pointer is all there. And do we actually have call frames? I wonder... Call frame. I'm not sure exactly. Okay, so we do have frames in the VM. Let's look at the VM object really quickly so I can show you what's in there. So in the VM object, basically just all the state for execution currently. We have a memory manager. We have the call frame. So that's sort of like a maximum number of frames, which since we use tail call optimization, we don't really consume that much of it in a lot of cases, which is good. The number of frames currently, then the value stack, which has its own limit. And that's the values that are being used for computations currently, and also the current functions that are being executed. The pointer to the stack, top, because this is a stack, you want the latest value that got pushed in. Then some other stuff that we are all holding on to. We can talk about some of these other things another time. But we do have an array for call frames. So we have access to that set of call frames. And that's a more traditional call stack based approach because you can trace back in the call frames, and whenever you finish executing one function, you just return to the current call frame that invoked that function. So instead of that, what we need to have is a function to call next. So you don't necessarily need call frames at that point. You might need your activation context, which is a kind of a concept for continuations. Continuation activation context. Well, that's not what I was looking for. Okay, anyway. Getting a lot of unrelated stuff here. Anyway, the idea is that at the time that function is called, you have a certain environment, like your lexical scope and maybe some dynamic scope. And that's represented as a closure usually. And then you might also need to have the continuation function that you're going to call back into for the result value. So instead of having an array or basically a stack of call frames, you might have more of like a linked list. Because if you have a continuation that gets passed around, then that continuation needs to know where it came from originally, I think, even if it doesn't go back to that original call frame. You kind of need that for debugging purposes. So a continuation would have a link to its previous continuation frame, because it's not like a linear execution anymore. Continuations make it so that you've got various different branches of execution at that point. Seer says, could you do continuations by just allocating a new stack and switching to it and then have the continuation object be a stack? Yeah, that's basically what I was just sort of thinking of, like a linked list or a stack. That's a good point. So we'll try to model that in a little bit if we make a little bit further progress on that thinking. So to set up a call, you would need the continuation for returning. So maybe it's just you do need the functionality of call with current continuation internally in the compiler all the time, because you need a way to create that object that can be passed on and then invoked to get back to the previous stack frame. Hey Ross, nice to see you. Ross says, don't forget that conceptually speaking, undelimited continuations proceed all the way to exit. That's the reason why Racket has with prompt. That's a good point. I forgot to bring up delimited continuations. I guess you have that versus undelimited, because I don't really know the difference, to be honest. Is a slice of a continuation frame that has been reified to a function. Unlike regular continuations, delimited continuations return a value and thus can be reused and composed. Control delimiters. Let's see. So am I right in assuming scheme does not have, let's see. right, so this is like an improvement on the idea of schemes continuations, it seems. Right, I think I've seen some of this stuff before. I just haven't really digested it. I think we'll start with undelimited continuations, and then maybe we can move on to delimited at some point if it makes sense. But if it's better, I would like to implement it because I want to have all the best and coolest stuff in this implementation. So what Ross was saying is that the undelimited continuations proceed all the way to exit. So that basically means everything that you call needs to be a continuation all the way through. But if I'm calling into C functions, yes, basically an undelimited continuation doesn't return. It's like an alternative forward path. Yeah, that's sort of what I'm thinking right now anyway. It's just that you have to have a continuation function to invoke to return the value of the current function or whatever expression is being evaluated. So then, what we need is for each call, we're going to have to create some kind of object for the continuation. I don't know if we can do this super efficiently, and maybe we just have to do it the naive way at first and then eventually improve it. So that's not the worst thing in the world to do. So if we were to have a continuation object, let's jump over to vm.c. Oh, we're already there. Actually, we want vm.h. And we have call frame. So a continuation would be very similar to a call frame, I think. If I were to paste this. And then we have a closure for the continuations, basically the function that we're really going to invoke. And an instruction pointer, because we need, well, do we need an instruction pointer at that point? For the general execution we do, but you wouldn't jump back to a specific instruction pointer location because the continuation already represents that. Slots, I need to figure out what I was using slots for because I don't remember. Come on now. Is that for, that's for the up values. Right. Okay. So the slots are sort of dictating what local values there are, and references to outer scopes that then can be turned into up values, which are effectively just wrappers around closed values. Ross says it might help to look at racket docs, especially about prompts. Delimited continuations are quite a bit more useful. Yes, I would like to do that, but I still need to wrap my head around undelimited continuations fully before I do that, I think. Okay, so total arg count. So if we were to use a continuation instead of a call frame, obviously OP return would not be there anymore. And we go back to VM call. Go down to the bottom here, but we're sort of setting up the call frame. In this case, virtually every call becomes a tail call except for any call to a function that's defined outside of Mesh, because you would need a, well, you wouldn't need a stack per se, because you're only making one call to a foreign function. So maybe you just need some basic information. You don't need a stack for that, but at the location of OP call, Zier says, do you even need to change a function call return if you're just allocating a stack and saving the position in bytecode? Surely it's basically a thread switch at that point. If you don't have call with current continuation, I think you could model it like that. But if you do have call with current continuation, I feel like it might be not as easy, but I would like for it to be easy if that were the case. Ross says, also various racketners have given good talks, which are on YouTube, e.g. at Strange Loop, worth a watch. Yeah, I'll definitely take a look at some of those. All right. So let's go back to my notes. So call a function, returns to computations. Let me just put some different notes here. So how to change the current design. OP call and other specific instructions, evaluation patterns must create a continuation. But I think maybe what Zero was saying before does make sense, where continuation doesn't have to actually be a new function entirely. It could just be the same function where you do jump back. If you can just reify the call frame where you were and then jump back to a specific location with the instruction pointer, because everything is sort of set up in evaluation that way. So if you were to create a continuation with the current design, to have call CC for the current design, wrap a call frame, or let's say let's do this. Make a call frame callable internally. So basically, if you have a call frame, then this would make it possible to resume the function at the current IP using the return value that is passed. In fact, you may not even need to pass the value. You can just leave it on the value stack. So if you can make a call frame callable, then that generalizes the approach of returning to some place in the computation, I think. Then your top level function, which is already an anonymous lambda, would have a call frame, so you can get back to the top level if you needed to. Make it possible to resume the function at the current IP using the return value that is passed. So basically all call frames would need to be, tracked in the garbage collector. Because they need to live longer. We may not have a stack of call frames anymore. We may have more like just objects that are linked to. So if a call frame is callable, that means you're just gonna keep running where it was. And the problem with that is that if it's already on the value stack, well, it won't be on the value stack. So because continuations are tail called, the original call frame will no longer be on the value stack, because it shouldn't be, because we basically replaced that call frame, but it's still reachable because it's been turned into a continuation object. Okay. So that means that you can to get back to the original call frame, emit an OP call, and VM call will, there's a function that knows how to dispatch on type. Okay, VM call value. So here in this VM call value function, I would have to check for a continuation type. Dispatch to the original call frame. Hello, Eric and Frederick. Thanks so much, Frederick. I appreciate it. Eric says, new time to stream, I see. Yes, we're streaming in Europe time right now because it's daytime for me, and it's a little bit more convenient. Okay, so this actually sounds pretty good to me. This might be a decent design to approach this, at least in the beginning, because we already have call frames. And if we go back to look at the definition of call frame in vm.h, we have our instruction pointer. We already have the ability to have this as a closure. The only thing that we may need to consider is whether this affects scoping at all. Like anything in the closure, if that would be negatively impacted. But I don't think so, because the slots, well, yeah, before we turn call frame into a continuation, we would have to make sure that we have access to all the things in its closure, because otherwise they're just going to go away. But maybe we're doing that in OP return already, and I can just sort of steal that code. So at this point, let's see, where was it? Close up values. Close out up values for any function locals that have been captured by closures. That's kind of a problem, because technically speaking, the values that are being used, or sorry, the lexically scoped bindings that are being used in the remaining parts of the function need to be available on the value stack at the time that we are resuming this function. So we might have to look into that. So let me just put that in the notes also as something that we might need to look out for. Things to watch out for. How are lexically scoped bindings, which are used later in the function, affected when we replace the call frame? Do we need to be careful to capture them before they get wiped from the value stack? It's likely we'll need to do something about that. Brian says, I'm new here. What is Mesche? Mesche is a Lisp language and compiler that I've been working on, basically inspired by Scheme, and it's just a fun project for me. Something cool to do. Dan says, peak hour home commute Sydney time. All right. Okay, so I'm feeling pretty good about this. It's something we can do. So if we make a call frame callable, do we need to wrap that with some other type of object, I wonder? Because call frame has a lot of the information we need already. As the argument count has slots. Yeah, if we were to reify this function and continue executing it, and potentially continue executing it again, we're going to need all of the captured bindings stuffed into the slots list here. Because otherwise, we're not going to have access to them anymore. They'll be gone from the value stack. So that's for certain. So anyway, if we make call frame callable, then we can just resume at the instruction pointer. I think that VM call, we would need a lower level version of this, like VM call frame, that can invoke, or at least start execution for an existing call frame. Because right now, okay, right here we are doing reuse of the existing call frame. Actually, that's kind of interesting. So when you call another function, we don't want to do this though. Right now, this is actually overwriting the existing call frame. Copy. So we still need to have this functionality here to basically replace the current call frame. But then again, Ross says, excuse me, I think I remember reading that continuations are easiest implemented by using continuation passing style throughout the interpreter VM, but I might be misremembering, i.e. not mixing paradigms. Yeah. It's good for a variety of reasons, but I'm trying to think of a way to do it that sort of fits in with the existing design here. That may be a mistake. We're going to find out pretty fast if it's a mistake or not. So we need to copy out the existing call frame before we replace it. We need to replace it because we are trying to do tail recursion here, or tail call, where we don't consume a stack frame. But when you're dealing with a model like continuations, you don't really have a call frame stack anymore, or at least not one. So I wonder if that even makes sense. Should there just be a current call frame that the VM holds onto? And a frame could potentially have a reference to a previous frame. They're going to have to be on the heap anyway. Yeah, so if we just get rid of the array of frames, then it doesn't matter because we're just holding on to a pointer to a frame that's been allocated somewhere. It's definitely more efficient if everything's an array. But then if you don't have a single stack anymore, because you have different points where execution can resume, then it doesn't make as much sense to store it like this. And this is not the performance sensitive part of the code anyway. The value stack is the more performance sensitive part. Okay, so what we need then potentially is let's see, VM. What am I using? Make as a, yeah, make. VM make call frame. What parameters would that need? So if you make a call frame, we can actually look at it right here. So we're just grabbing one of the frames that have already been allocated on that array, setting the closure, IP, and slots. I mean, really, you don't need to initialize IP because it can be done inside of the closure. So we need to pass the closure, the number of slots, and the argument count. So it was a closure, slots, args. Oh, okay. Slots is actually a pointer to the value stack. I forgot about that. Arg start is a pointer to the value stack where the first argument to the function can be found. That's fine whenever you call the function initially, but whenever you call something else or you need to create a continuation, then you're going to have to grab those values before you call something else. Though, this only matters for calls. Calls are the only point where we need to start doing some cleanup. Anything else like a begin expression, if expressions, anything else like that that don't cause a call to another function, we don't need to worry about messing with the values or the bindings that are being used in the closure. So that might be a way to keep this a little bit more efficient. We can just wait and copy those things off the value stack at the time we're about to invoke another function somewhere else. think this could work. There are some other things we'll have to think about later, but I'm not going to worry about discussing those at the moment. I think I have what I need to start writing some code, I believe. So I'm going to take a, let's say like maybe a 2-minute break, and I'll be right back and we'll get started writing some code. All right, let's get to it. So like I was saying, we might change this design so that we don't have an array of call frames anymore. So let me try to get started with just, we'll do this one step at a time. I'll try to run some tests just to make sure everything is still working the way it's supposed to. In fact, let me make sure that I can run the test in a very clean way. So I'm going to use compile here, and I'll change how I'm going to invoke this. I think I can run test.sh if I'm not mistaken. This may be source, so let's go /test.sh. Okay, no manifest.scm. I believe there is one. Oh, right. Okay, let's do it here. Okay. To see what it does. I wrote my own little test runner in C. It's trying to update the Geek Shell environment. Oh boy. Anyway, I wrote my own little test runner in C. Test.sh is not a real script, but the idea is that you know, it's just a typical test runner with asserts. All right, cool. Let me go back to the parent directory, try to run and compile again. It's run-tests.sh. Let's see, what did I do wrong here? I think I compiles if expression. Yeah, I screwed that up because I changed the code. Let me go into Magic here. Let's change that. Just take it back out, run it again. I don't know why it's seg faulting, unless I change some code in vm.c and it doesn't like it either. Nothing obvious. Okay, it doesn't matter right now. As long as I can get, well, it does sort of matter. Compiles module import. That's kind of interesting. Hey, Travis. West Coast of the US here, up late because of Labor Day tomorrow, so get to catch this live. Well, nice to have you. It must be super late there right now. Let's see, what does world clock tell me? It says in Seattle it's almost 1 a.m. So yeah, super late. Let me see. I don't know why things are failing. It could be any number of reasons because, you know, it's been a while since I actually worked on this code, but what we really need is to test that we can change the execution model and everything still works after. So let me go into the test main.c. I'm going to turn off the scanner and compiler suites because I don't have another way to turn those off. I'm just sort of, you know, commenting out code, which is fine. Let me see which function is failing. So returns basic values, calls function with rest args. We're jumping into the deep end. Caused by read memory access. VM.c 821. Interesting. So one thing I can do to figure this out is to go and turn on tracing of what comes out of the compiler. Okay, modules are doing something very wrong. That should not be happening on the stack. That's hilarious. What is going on? So we're resolving the mesh list module. Makes me wonder if this is something I fixed at some point. Okay. Let me go back to the test code. Okay, so I am actually pulling in mesh list here, which is a really bad idea in a function that happens so early. Okay, I think the problem here is that the stack is being consumed because it keeps adding the module to the list, which is weird. I haven't changed anything. I don't know why it would be doing that all of a sudden. All right, let's just take this out. Don't ask me why. Okay, so still doing the same thing. That's fine. How tall is a stack? Yeah. Okay, that makes sense. I think I'm using a very small value. Yeah, uint 8 probably for the size of the value stack. Would that be in vm.h? Frames max 64 times uint 8 count. Uint 8 max plus 1. Well, still, it's probably the call stack that it's getting freaked out by. Ross says, I'm getting crazy buffering. Oh, that's not good. I don't know what part of the chain that would be coming from. Ross says, in C, one way to do that is using a trampoline in your apply functions and not really throughout because it's mostly a function application thing. Yeah, that's true. That's very true. Okay. Let me just get that function out of the suite really quick. Let's see if it keeps happening. Okay, so the rest of them are passing just fine. All right, well, we'll comment that out for now. I'll have to go off stream and take a look at what's happening with it. Okay, so the point is we want to have a function, or at least, let's see, evaluates let, imports modules. We'll just take everything out. Here we go. Evaluates tail calls. I think this is a pretty good example to try because we're tail calling the same function, which is kind of interesting when you think about continuations. Let me think about how this would look. Because technically it is just resetting the call frame to itself when it does this loop. which in fact is a little bit inefficient. I probably shouldn't do it that way, but for the purpose of what we're looking at right now, it's probably fine. So we have an if expression, we call loop, and then you would return the continuation for loop, where you would call the continuation function to return the value back. When we do the recursive call, you're basically calling the call for its own call frame again. Yeah, I think I should for self recursive functions, I should probably just make that a jump. If I haven't already, I'm pretty sure I didn't. So how about this? Let's do another function that doesn't do a recursive call, because maybe we want to see just a normal style of function being invoked. We'll have two functions. Define alpha x, vita x. No, it's not vita with a V, it's vita with a B. That makes sense. And then alpha would call, let me do it the right way here. Vita with 5, let's say. And then we have, well, we should probably put this after, right? Let's put this right here. Whoops. And then on the loop, we can call alpha. I don't know. Let's do this and see what happens. X plus 1. Vita. We'll still use this. If not equal x 5, then maybe I can return 0. Otherwise, return x. That might be okay. That's something that could possibly be evaluated. Evaluates calls. We can just call that. All right, let's run it. Failed. Expected kind value number got 4. Interesting. Let's take a look at what the output was. Okay, we defined alpha and vita here. And then it returned. Should have executed. I think I must have missed a closing paren. No? Find alpha x, alpha 1. Interpret OK, value.kind. And this is probably just going to be 0. I think. Or it could be 2. How about that? Let's just make this 2. Make it clear what's happening. So we're going to pass in, whoop, no, that's wrong. This needs to be 1 because we're adding 1 to it. Okay, run it again. Still failed. Expected value number got 4. Let me check. What did I do wrong in that case? It's in value.h, value number. Where is the enum? Okay, so 0, 1, 2, 3, 4. Is it got an object instead? That can't be right. So it's probably returning a closure somehow. I'm calling alpha at the end. So that's a let. em eval. So how this test works basically is I'm just calling this macro that takes this input string and then goes and compiles it, and then takes the function that the compiler returns and executes it, and then at the end grabs the value at the top of the value stack and then just checks it. In this case, I'm not getting the thing that I expect. I've got some function to print out an object. Let me go check on that because I haven't used it in a while. So in object.c, mesh print, mesh object print. Okay, that's what it is. So if I go back into test VM, I'm pretty sure this is going to tell me it's function alpha here. I don't know why it's sitting on the top of the stack because I'm calling it. What if instead of that, I do this, 5? Not executing the whole thing. Am I doing the right function? Yeah. Oh, all right, that's a problem. Not good. Okay, now it passed. So we have 2 at the end, all good. Everything is the way it's supposed to be. I just forgot a parenthesis in there. That typically happens whenever you're not writing code in the right type of file to catch these problems, because I'm just doing it as embedded C strings. All right. So now that I have a baseline here where we have some stuff happening in this function, I can start changing the behavior of how function calls are evaluated and how values are returned to the previous function call, and then at least see if we're breaking things or even see if there's any crashes. So then let's go back into vm.c, and we can try to change first. If I were to change the frames here, call frame, current frame, make this a pointer. Not having frames anymore is going to result in a lot. Wow, that's not right. I should have gotten some syntax errors because I'm using frame. Oh, because it's the header file. Interesting. Okay. I'll go change something in the actual code too to make it pick it up. So frames. So we got frames in a few places. Frames. Yeah, quite a few places. I don't know why it's not following where I'm clicking. So let me go to, what is it? Fly check error, list errors. Is that right? Fly make? All right, there we go. No member name frames. That's in this function here. Should probably make this show up in my popper buffer because it's too much code here. So for runtime error, we actually just need to look at the current frame. So in this case, I could say VM current frame. So pretty much any location where we're looking at a frame, we can just do that. I might just go back and clean up the code at some point, but that's fine for now. VM, oh, let's do this. VM frame. And, this makes me think we probably need a pointer to the previous frame. So inside a frame, when you call a function, the new function should have a pointer to the frame that called it. Still doesn't help though. Let me take a look at what I do in the garbage collector, because I need to see how I'm keeping track of other objects. So maybe we do need the concept of a continuation object to hold on to a call frame, because it needs to be an object so that the garbage collector can traverse it. Yeah, so I don't have a list of, or an array of call frames anymore, so I need a way to keep track of all the sort of active frames, since there can be branching computation and continuations that are sort of just hanging out there. But when you think about the way that functions are being called, some function had to call some other function. And if that, if a function isn't if the function is not responsible for calling another function in an active chain of function calls, then it can be garbage collected. But how do you know when it's time to do that? I guess the function reaches its natural end, then you invoke a continuation and not a function, which I know are supposed to be the same thing, but the idea is that if you're calling a function that has not been called yet, that needs a new continuation frame, or needs to have the call frame be stored. Okay. Let's try to go with something simple, and then we'll see how it falls apart. We may need to do some stress testing on the GC to flush out any issues with call frames being cleaned up before they need to be, which is not very hard. I have a flag for that in the compiler. So there actually needs to be an object that can encapsulate a call frame. So maybe if we go to object.h, we can have another type. So we already have closure. We can have a continuation object that might hold that call frame. Let me look at call CC. Taking a function f as its only argument, call ccf within an expression is applied to the current continuation of the expression. So effectively what that means is that when you call cc, you pass it a function that can accept the continuation function. Is that right? Ross says that Firefox is causing the buffering. Yeah, sometimes that happens. I don't know why. Taking a function as its only argument within an expression is applied to the current continuation of the expression. For example, call ccf e2 is equivalent to applying f to the current continuation of the expression. So what's e2 in this case? Is that environment 2? So you would pass a function. Call ccf is lambda c e1c. So the whole expression is equivalent to f. In other words, in other words, it takes a snapshot of the current control context or control state of the program of the object and applies f to it. Okay. Continuation object is a first-class value and is represented as a function with function application as its only operation. When a continuation object is applied to an argument, the existing continuation is eliminated, and the apply continuation, tail call elimination. Apply continuation is restored in its place so that the program flow will continue at the point at which the continuation was captured, and the argument of the continuation then becomes the return value of the call CC invocation. Continuations created with call CC may be called more than once, and even outside the dynamic extent of the call CC application. Yes, exactly. All right. So you call CC, you give it a function. That function takes in the continuation as a parameter. And the reason why I'm looking at this is so that I can tell how I need to model this stuff internally. So if the user passes in a function to call CC, then the thing that they receive is the continuation. So we're basically invoking a new function, which makes sense because we're trying to replace the execution at the current point with some new function that they can then later call that continuation. All right, so we do need continuation to be an object. So let me go up to where closure here is. Just need to copy some bookkeeping function stuff here. So we're gonna replace closure with continuation. Oh, no. All right. So we got is continuation, as continuation. And then we also need to have a record type for a continuation. Let's see if I can find. So we got closure here. I'll copy this. And then I'll put continuation here. We don't need module. We don't need function. We really just need a call frame, which is not an object. Or I can say frame, I suppose. And then object function, don't need that. Up values, up value count, we don't need that. So the frame itself does the frame in vm.h. It has the closure. So the closure is already captured as part of that. Okay, that's good. So then we probably also need the previous continuation. Object continuation parent. Probably not the right name for that, but that's what we'll go with for now. When we create a continuation, we need to store the current continuation as the parent. So that we can do garbage collection. We can walk the chain of continuations basically and mark them. It should not be used for any other kind of calling back into the parent, I think. It makes you wonder whether call frame here should not be a pointer, if it should actually be a struct, because you need that information to restore the continuation the way that it exactly was. So you don't want to depend on another object, I think. So then instead of the VM holding on to the current frame, it actually needs to hold on to the current continuation. This might be fairly naive, but we can improve it after we see whether it works or not. Okay, so then back in vm.h, instead of the current frame, get rid of this. Whoa. We will get rid of call frames. In fact, we can have an object continuation, current continuation. That's too long for a variable name. But that's fine, because, you know, we need it anyway. And then call CC basically is just going to hold on to this value of the current continuation and then invoke a new function and then pass it as a value. So that works pretty well. Okay, so frame count. We don't really need a frame count anymore because it doesn't make sense. Okay. So then, oh, take that out too. Let's check the code, make sure I didn't delete anything I didn't mean to. Okay, call frames and then frame count. Fine. So we're definitely not going to get to a point where the code runs again today because I'm changing so many things that it's probably not going to compile, but we'll try to get as much as we can done. And then on Wednesday, we'll come back to it and maybe have some time to get it working. I might spend a little time before then too, just, you know, playing with some stuff. Okay, so let's see, back to object.h. We have the continuation here. We have the enum value to identify it, basically the tag of the object. And we have our function to check to see if something is a continuation, which is good. We also need to add some stuff in object.c for printing out a continuation. So if we look at where closure is, we can say print function. We're going to do a similar thing for continuation where we basically say it's a function because it's effectively a callable at this point, so we can treat it like it's a function. But maybe we need to print it out in a way that makes it obvious what it is. Closure is fine. We don't need to really know that it's a closure, but for a continuation, it would be helpful for debugging purposes to see that it's a continuation. So we have print functions for things like print function. Where is that? All right, so for a continuation at least, I say print continuation. Continuation. And then we don't have any names here. We're just going to print out the... We could do something similar here. Let's see what I can do. So printf continuation OX, and then a pointer to the continuation object itself, continuation. And then we want to check the function that's inside of it. So continuation frame dot function. Let's see. So call frame has closure. All right, this is getting a little bit dirty, but that's okay. So object function is continuation. Come on now, continuation frame dot closure arrow function. Yes, that's a recipe for disaster, but that's okay. Oh, whoops. Function equals. So let's just go back to what we had before, and then we can print this out similarly. Just have this little suffix. We're not printing the name, are we? Name is null. Where do we print the name of the function? Ah, right here. Okay. Okay, that's good enough right there. So that should give us some information about the continuation. Why is this not happy? Must use struct tag. I think I need to go into value.h and do a type def. So object closure. Yeah, I need to do a type def for continuation here. Got a little bit of some circular references and types, so we have to do some magic. Continuation. This is not a convenient word to type, I have to say. Okay, so now we got all that stuff wired up, and the VM has a handle on the current continuation. That's all good. The execution path. for mark routes, I think we may need a function for marking. Oh, excuse me. We could probably just mark the continuation object directly. So where is the rest of this? I'm just going to change this right here. So mesh, let's just delete that, put that up on this line. And then here we can say VM current continuation. Now we're gonna have to add some code for doing the garbage collection correctly. So if I were to go to mark object, we will check the type. So if it's not a string, okay, add the object to the gray stack if it has references to trace. And if it's not like an essential type. Okay, so now let's look for trace references, darken object. Here we are. This is the place we need to be. So I'm basically just updating the garbage collector so it knows how to walk the references of the continuation, so that we can mark everything that it reaches. And continuation, we need to pull out the closure from the frame, I believe. Effectively, we just, wait, hold on. Yes. Continuation, no. What is this not happy about? Incomplete definition of type, uh-oh. I hope we didn't run into some kind of weird issue here. So we don't need up values here. That will be taken care of as a part of the closure marking. Okay, so that's not happy anyway. Let's go back to, I'm curious if we're gonna have any issue with compiling this, because I don't know what that error is about. Invalid use of incomplete type def, aka struct object continuation. All right, I think the problem is I have another typo. So let's go back to value.h, continuation. Here we go. All right, that's better now. Ross says, Firefox is wigging out. I think YouTube live streams are too much for the laptop. Oh boy. Well, hope you're able to watch it later. I'm happy to hear any feedback you have, Ross. Thanks for joining. All right, let's go back into, all right, we're in VM.c. I think we're good now on this line. Let me just update the line to refresh the diagnostic. Okay, so that one's fine. And we have all the other current frame related stuff. Okay. I think what we're doing is right though, because we do want to have access to the current continuation for debugging purposes. Like let's say an error occurs, you want to be able to stop at the current continuation and maybe step through it. So you would need to know what it is. All right, so frame count is no longer necessary to reset the stack. When do we call reset stack? Reset stack. I wish this thing would follow whenever I'm arrowing through. VM runtime error when we reset the stack. And what that function? The function just sets frame count to 0. Okay. So effectively, you would want to set the continuation to null. in this case, which is not the greatest thing in the world, but that's fine. Runtime error, current frame. We need to pull that out of the current continuation. So current continuation dot frame, and we need to give an ampersand on that to give it the pointer to it. Let's see what's going on with that. That's correct. And we have a few more errors to deal with here. We're gonna stop probably in about, let's say about 15 minutes. So let's see how far we can get through this. Let's go to the error list. No member name frames, and that is in the tail call function. So this is kind of an important spot where we need to think about it a little bit. Eric says, what is it that crafting Emacs uses to do code completion like with YaSnippet, but do we use YaSnippet or something else by default? I don't know, because I'm not using it right now. I think you should check, maybe you should ask on the repo or maybe in the Discord, I think. Jeff knows better than I do. Okay, with call frame here, this is sort of the place where we need to create a new continuation, I think. So even though it's a tail call, a new continuation based off of the current one. And we need to close up values for the current continuation. And then set the VM to use the new continuation. But we also need a reference to the continuation to call for return. So that's something we don't have at the moment. So maybe that's something that goes in the continuation object itself. Let me think about that for a moment. If it needs to change ever. Yeah, whenever you create a continuation, I think that's right. So that sounds right to me. So pass the return continuation of the parent into the child. So I think that's one thing we will need here. Is not, well, is that right? Let's take a look at the object definition again. So object continuation return. I can't use that, huh? Not a great name, but the idea is that we need to have a pointer to the continuation that this continuation will invoke whenever it's finished. So if you can imagine a function, excuse me, that's executing, it needs to know what continuation to call back into whenever the function is complete. So we need to hold a reference to that, and that continuation is going to be the it's not going to be the parent, because the parent would just be like a call stack. What we need is a way to thread through a continuation to call back into that comes from somewhere else. So if you just have a simple program that's not using call with CC, effectively you're just going to be passing a continuation to the top level function. Or not. No, it won't be in all cases. You're not going to pass the parent in all cases. It depends on where it's supposed to return to. All right, so a call in the VM The return to would be the previous continuation, because you need to return to wherever the value came from. But for certain types of code, you might be passing through the same continuation through multiple layers. But maybe you actually need to have compiler optimization to figure out that you can do that. Okay. So we can think about that another time maybe, but for now at least this is sufficient to continue. So we need to create a new continuation. So what I would do here is object continuation. I also need to have a mesh object make that with the, let's see, continuation function, which I don't have yet. If I go to object.c, oh, how many object.c's do I have open here? Object.c, which one is this? That's the right object.h. Where is the other object.h? Can't be the same one. That's weird. I've never seen it give two copies of the same thing in the buffer list. Anyway, in object.c, I need to look at the make functions. Mesh object make. All right, let's make closure because it's very similar to that. We're going to copy the definition of this function. This is basically just a function that does the allocation of an object of a particular type, in this case, a continuation. Mesh object make continuation. And we're going to pass into it. Don't need module, but we do need the function to return to. We also need the closure to pass to it. So we're going to have a closure and then object continuation return to. So if we go look at the what is it? I want to look at the shape of object continuation. So we have a parent, we have return to. Are they going to be different? They would be different if you were doing some optimization. In a simplistic case, they would be the same because always you would just say that whoever called me is the one that's going to get the return value. But at least with tail recursion, you could just eliminate that intermediate. Okay, so that's maybe how tail recursion or tail call optimization shows up in this case. Is that whether you need to have an intermediate return function for the continuation. Hey, Emmanuel. No, that's not Friday already. I mentioned on Friday in the stream that I would be doing some experimental streams in the middle of the week here. We're just doing some live coding. Okay. A couple more minutes and we'll be done for the day. Okay, so for now, let's just assume they're the same thing. We will need to change that. So we can allocate an instance of the continuation object if I type it correctly. All right, and we're going to allocate a continuation with a type of continuation. And for continuation, we need to initialize the call frame. So we need some of that code we had before. So maybe frame.ip equals closure. Let me go back to where that was. Where is that? It's in vm.c. We set it up right about here. This is the kind of thing we were doing. So frame closure is closure. Closure function chunk.code. I didn't really explain what chunks were, but they're basically just byte code, lines of byte code, basically, that we have a pointer to in memory. Up values, I'm not really worried about. We already have a closure here. Slots. So continuation frame dot slots equals. I'll need to grab that too, I think. So frame slots. What is that going to be? A value slot start or value start. Arg start. Okay. Then we return the continuation. All right, so in theory, this would work. I also need to set some pointers here. So continuation parent is return to, and then return to is return to. This may change entirely. To do these will not be the same in practice. Depends on optimization. Okay. So that looks pretty good for a function here. And then back in vm.c, just for the base case, we can say vm current continuation equals mesh object make continuation. I believe anytime I call that, I'm passing VM in. Okay, so VM. And then I want to pass in closure. And then arg start -1. And also use the parent. Where is the definition again? Maybe I should swap the... let's just leave it like that for now. So then the next thing I need to put in here is the VM current continuation, because we need to return back to where that is. Okay, so now we don't need this part anymore. In theory. Frame total arg count. So continuation frame, yeah, that's right. That's it. It's gonna be VM current continuation. Whoa. Okay, that should be happy now. And this function also needs a signature defined. So let me copy this signature and then go into object.h, make closure. I'll just paste in the signature here, take out the bracket, and then that should be better. Okay. So we have the ability to allocate a continuation at the point where we're calling another function. We would do the same thing for tail calls, I think. I think that I'm coming to realize that the difference then between a tail call and a not a tail call is that for a tail call, you pass the parent. The current continuation has a return function. You just pass that along to the tail call. I'm pretty sure that's what this results in, which makes me happy then, because I already had implementation of tail call optimization, so it should just be the same thing. So then if I just do one last thing, I will go to VM call where we started. And here, interesting, we're copying the frame slots. It may take a little bit more effort to update this one, I think. So we won't do the continuation just yet. We're gonna allocate a new call frame. So we don't actually need this. We don't reuse the frame, we reuse the return function. So firstly, we can close the up values for the frame and the current continuation. And then frame.slots, this probably needs to be a reference. Okay, so what is the problem? Oh, current continuation. Okay, something's unhappy here. I've reached into this thing before. I don't understand. Current continuation. Current continuation arrow frame. It's not dot. This arrow. Something must just be upset here. It doesn't make any sense to me why this is complaining. Close up values needs VM close up values. It needs a pointer to a stack slot, and slots may actually be a pointer already. So let's go back really quickly to VM.h. Slots is already a pointer. Okay. So we close the up values. We're copying the slots down. We don't need to do that anymore, I think, but we need to understand how this affects the value stack, because this is what this is doing. It's clearing off values from the value stack. That might actually be okay. Okay, let's do this. VM current continuation frame dot slots. This probably needs to be updated. Current continuation frame dot slots. And then set up the closure and instruction pointer to continue execution. I think what we need then is to just create a new continuation like this, and also update the total arg count. So drop this right there as well. So we're making the new continuation. We're using the closure. We're using the current continuation as parent. But what we said before is that we, instead of using the current continuation, we would use the return to of the current continuation. Use the function of the parent continuation. Because the current, because the parent can be optimized out. All right, arg count plus num keyword args. All right, so this goes away, this goes away. Arg count plus num keyword args, that also goes away. And that's it. So in theory, that would do the job if I had all the rest of the code updated and tested it. But we don't have time for that right now. Eric says, I'm getting my Steam Deck within a few days now. Seriously, can't wait. Well, those sound pretty cool. I don't know that I'll get one, but they do sound pretty cool. All right, so we made some progress today. I feel pretty good about what we did. It's not working yet, but we've written some code that's a good foundation for what we need to do. And then on Wednesday when we stream, we might be able to get the rest of the implementation working to a basic degree so that at least we can see whether this change to the VM is going to work. And then if it does work, we might be able to implement call with current continuation, because it's pretty clear how we would do that if this actually works. So important things are making sure that garbage collection still works correctly, making sure that capturing bindings in a closure works correctly, and making sure that execution continues correctly when tail call optimization happens, because that is a little bit more complicated of a situation, I think. But I'm pretty happy with what we've done so far. I feel like I have a better handle on how this should be implemented in Mesh using the stack-based VM. And I'm looking forward to working on it again on Wednesday. So thank you all, those of you who joined today. I'm surprised at how many people were here. Really cool to see people interested in seeing more about this. So hopefully you'll come back on Wednesday at the same time and join me again whenever it happens. So thanks everyone, and we'll see you next time. Happy hacking.